Welcome back, everyone, to the International Sport, Health and Emerging Technology Summit Conference 2021 keynote session. Again, before we start, I'd like to remind the audience to kindly mute your microphones whenever a talk or lecture is in session. If you would like to post questions to the speaker, please utilize the chat box on the right side of the Google Meet. You can post questions in the chat box during and right after the presentation. And at the end of each presentations, I will read out the questions to the speaker. A brief introduction on our speaker for keynote lecture number 9. He is currently a professor at Loughborough University, United Kingdom. He is also the chair in Environmental Physiology and Ergonomics and the director of the Environmental Ergonomics Research Center. He started his career in 1990, working at the TNO Human Factors Institute in the Netherlands before he joined Loughborough University in 1998. He was also the Dean of the Loughborough Design School between the periods of 2015 till 2018. His research covers two main topic areas, one being human thermal physiology, environmental ergonomics, and the other being heat and vapor transfer through clothing. Ladies and gentlemen, without further ado, let's give a warm welcome to Professor Dr. George Havenith with his presentation entitled Improving Sports Performance and Sports Clothing, Working with the Sports Industry Towards Better Products.
I would like to start by thanking the organizers for inviting me. And with the invitation, the organizers asked me to talk specifically about our cooperation over the years with sports industry, which was aiming at improving sports performance of their top athletes, as well as improving sports clothing for the consumer market. So we've been working with in the sports industry for quite a long time. And the main links that we have there that are public is our work with Adidas and our work with Decathlon. We work with other companies as well, but they are confidential, so I can't name those. So as I said, we work with these companies for a long time already, and we're cooperating with over 20 years with Adidas, for example. So to just give you an idea about the type of funding, so the main funding from these companies comes through PhD student funding, where they fund 3 to 4 year PhD grants, and the students work then on topics of mutual interest. And some of the topics that we've been working on through PhD students is the impact of body cooling, of muscle heating, of body mapping temperature sensation and mapping moisture sensation. We've been looking at perception of fabrics, as well as thermal perception and temperature regulation in the children and also in the elderly. But there's a long list of other projects that have come through. So let me start to give you some examples of the work and start with the body cooling. So body cooling is important, especially when we want to keep the athlete working in a hot environment. And we know that heat in general has quite an impact on sports performance. And one of the theories linked to this is that is through sensory integration of afferent information from the different body parts, the performance is influenced. So for example, if the body core temperature gets very high, through sensory integration, the performance might be tuned down to protect the body. So several inputs we're familiar with. We have core temperature. We know that muscle temperature has an impact on performance. The impact from the feedback from metabo and mechanoreceptors is important. And finally, what's becoming more and more known over the last couple of years is that skin temperature itself has quite a substantial impact on performance in the sensory integration model. So the question is that if we know that we are sensitive to heat and that in heat our performance will come down, can we, by lowering the body temperature, benefit performance? So by cooling the person before they do the exercise, they would be starting at a lower level of heat content in their body, which means it might take a bit longer before they reach the high temperatures later on in the race. Simple approach, of course, is put people in an ice bath, but that's actually unpractical, of course, for field purposes. And so the question is there a more compact alternative approach to this? So this was a project we were working on with Adidas. And we started first with body mapping research to try to find out which body skin sections would be best used for optimal cooling or heat extraction in pre-cooling before a race. So the tools we use for that is this waterproof suit that you see on the right-hand side of this slide. And that suit is quite special because it is A, with very high density tubing, and B, it has 16 individual segments that we can control the water temperature individually. So here you can see the segments. So you see lower leg, upper arm, lower arm, hands, feet, front torso, back torso, are all separately perfused with water. And what we can do is we can measure roughly how much heat we can extract from the different area. And we do that by looking and measuring the water temperatures that come in and out of the suit. And with some calibrations, that gives us an impression of the amount of heat extracted. So these are some of the results from that study, and so some technical issues with this study, but this roughly gives an outline of the results, where you see the colors go from light yellow to dark red, and the darker red the color is, the more heat was extracted. And this was in resting people. So you see typically here that the hands and lower arms are very powerful in terms of heat extraction. The legs are quite powerful as well. And then it's reduced. The front torso was not very effective. The upper back was quite effective. So having this map, Adidas then developed a cooling system that athletes could wear during the warm-up. So in the warm-up they're supposed to heat up the muscles, of course, that are active. So for a cyclist, that would be the leg muscles. But by trying to keep the rest of the body cool, the body temperature then pre-race would stay lower and would give a bigger margin for heating up later on. So here you see the product. This is actually two stages of the product in the two images. And you see these are sleeves which cover the hands and the lower arms, as well as a vest covering the upper torso. And you can see in it, it's a material that absorbs water. And in the thicker patches, the padding that you can see, there is a gel in there which absorbs water and then slowly releases it. So there's cooling from the evaporation of water from those areas, but also the whole sleeves and vests ensemble was also pre-cooled by putting it in a freezer for a couple of hours. So we were sure that the temperatures there, that all the moisture inside was frozen, so it would have a lot more heat capacity to absorb heat. So to just give you an impression, so this is work by Broekhuizen in our lab. So what we have in the experiment, we have a baseline, a pre-test measurement. Then we have a warming up. So that's a cycling warming up and a time trial on the bicycle. And what you see in this slide is the skin temperature development during that trial. So the green one is the control trial. In this case, this was in 27 degrees Celsius air temperature. So in the control trial, you can see that in the warming up, the temperature first goes up a bit, but then starts to come down slowly, which is related to sweat production and sweat evaporation. And then the temperature stays quite stable during the actual time trial. If we do the cooling, that's the blue blocks and blue line, what we see is that the cooling system that's warm up only in the warm up. Obviously in the time trial, we don't want to wear any systems. We're not allowed to wear any of these systems. So in the warm up, the cooling system is worn, and you can see that has quite a substantial impact on the skin temperatures, which are up to 4 degrees lower than in the control condition. So skin temperature is reduced. And ideally, of course, we would like to cool the core temperature as well down a little bit to give us that bigger margin. But in these experiments and in many similar experiments by others, we find no significant differences in core temperature. So core temperature is not affected, but skin temperature is affected. And that means that overall body temperature, which is a combination of skin and core, will have been cooled to a certain level. So we have reduced the body heat content, but not specifically core temperature. So then we have to look at the impact of this on time trial performance. And this was done in two sets of experiments, one by Steve Faulkner in our lab and the other one by Iris Broekhuizen at different temperatures. And here you can see the results. So on the y-axis here, we have the finish time for the time trial. And of course, the higher up the data are, the slower the trial is. So the red is the control data and the blue is the cooling data. And if we first go to 34 degrees Celsius and 27 degrees Celsius, we see significant differences between the control condition and the cooling condition, where in the cooling condition, the time trial was shorter, so people were faster. And in the first 34 degrees condition, that was by over 7%, and in the 27 degrees Celsius condition, that was 2.5%. Doing this at 24 degrees Celsius, we did not find any significant difference. So one reason for doing this work is to see down to what temperatures these kind of cooling devices actually has an impact. And here it's very clear that the impact stops somewhere below 27 degrees, and at 24 degrees we didn't have the effects anymore. So there's no benefit to use this at low air temperatures. So pre-cooling, even without body core cooling, has been shown to be beneficial, but only up to a lower threshold for ambient temperature. And of course, that threshold may depend on the cooling system. If you put somebody in ice water, of course, that might be more powerful than this. But of course, if you're in ice water, you can't warm up. So it has to be practical as well. So an alternative thing that we studied, so a completely different study, is actually, in some cases, it's worthwhile to add heat to the body. So if people are exercising in the heat, we tend to want to promote heat loss. So that's why we come up with this cooling. But in this example that I'm going to explain, we want to avoid heat loss. And the example here is track cycling, and can be applied to many other sports as well. So in track cycling, the athletes tend to warm up, like in all sports. Then they go into the race, but sometimes the race can be suddenly delayed. If there's, for example, an accident, as in this picture, suddenly the race will be delayed, and the athletes are usually waiting, ready to go on the track, and they're just cooling down while that happens. So they have put effort in to warm up their muscles beforehand, and rather than starting with warm muscles, the delay causes their muscles to cool down. So the question was, is it possible to keep the muscles warm? And in this case, that was done, or we attempted to do this, just wanted to study this by using heated trousers to keep the muscles warm. So the question is, how can we prevent Olympic cyclist muscles to cool back down after their warm-up? And this was done before the London Olympics, and the PhD student working on this was Steve Faulkner, and it was a cooperation between Loughborough, Adidas, and British Cycling. So in order to find out, you have to do two things. A, you have to look at the muscle temperature and see whether that's affected by the electric heating. And the second thing, again, you have to do a performance test. In this case, we need to target the skin directly over the muscle, because we could try to keep the whole body warm, but that would have a negative effect, because then your body core temperature might rise as well, and that could be detrimental to your performance. So we really want to only heat up the muscles that are important. And in this case, in the cycling, that's the leg muscles, of course. And so that's why this was targeting the leg muscles with the heated trousers that you see here in the previous picture. So on the top right-hand side, you see the insertion of a temperature probe into the muscle. So that was not worn, of course, during the actual performance trial. But we had two types. We had a needle probe, which we used in some experiments. And in this case, it was a flexible probe, which could remain in the muscle during the actual study before the performance test. So this was done in environmental conditions of 16 degrees, 54% relative humidity, which is of what you might find in cooler climates on the tracks for cycling. So people would do a warm-up to get the leg muscles warm. And they would take a 30-minute rest to simulate this delay in the race. And then we would do a wind gauge test where we would measure peak and mean power and time to peak. And we would measure the muscle temperature, the vastus lateralis muscle, at the depth of 3, 2, and 1 centimeters. In this first experiment, there were 11 semi-elite male cyclists, and we had a counterbalance design. So we had a control condition where people would not be wearing anything, just a normal tracksuit. Then we had a insulation condition, so people would be wearing ski trousers, thick ski trousers. And the third condition was that we would be wearing electrically heated trousers, which delivered about 7.5 watts per leg and are battery operated. And this was always, all these three conditions is what happens during the 30-minute rest period, looking at the cooling down of the muscle. So on the left-hand side, you see the needle probe for muscle temperature that was inserted to 3 different depths. And in most of the experiments, that was corrected for adequate tissue thickness. So we knew that we actually were inside the muscle at that required depth. So in this slide, we are looking at muscle temperature drop after the warm-up in the 30-minute rest period that we had between warm-up and race. And that's a relative. So we start with the muscle temperature that was produced in the warm-up, and then we looked at how much that cooled down. And this first blue line is the control. So that's with just wearing a tracksuit. And you see the drop in temperature is roughly 1.5 to 1.6 degrees Celsius. So that's a substantial drop if you think that the warm-up might raise muscle temperature by something like 2 to 2.5 degrees maximally. So what happens in the ski wear? So the ski wear reduces the drop in temperature, not massively, but it reduces it. And finally, the heated trousers reduce the drop even a bit further, and that's about a 25% reduced drop. So interesting here is that even the heated trousers are unable to keep the muscle at the actual temperature that was at the end of the warm-up. So let's look at the impact in the wind gate test. So here we have peak power of the wind gate test for control, insulated, and heat. And in this case, only heat was different from the control, and insulated and control were not different, although it's suggested there is a difference. But in peak power, there was a 9% increase versus control, and that's of course a massive difference. If we look at mean power that was delivered during the wind gate test, there was about 4% increase in mean power compared to the control condition. So these were much higher numbers than we expected. And when we talked to the athletes, and it's also has been quite extensively in the media, the athletes were really enthusiastic and they really felt that this was a really strong benefit to their performance. And of course, we were lucky that the British team at that time who had these trousers were actually really successful in the races, which of course we're not sure that's due to the trousers, but based on this evidence, it seems that they contributed quite a bit. So this had quite a bit of impact in the media as well. And so several gold medals were won with the track cyclists using this, Chris Hoy, Victoria Pendleton, etc. So we've seen that insulation and heating reduce the drop in muscle temperature and improves the sprint performance, whereas the insulation alone was not effective enough. So of course, disappointingly, we only were able to reduce the drop in muscle temperature by about 25%, and we're not able to abolish it. So one question was whether optimization is possible. So we did a couple of more experiments, and these are done by Margherita Recuglia, another PhD student, and we were looking at the optimization of the heating procedure. And there's a couple of issues with the electrically heated trousers that we had. So the first thing is you need to limit the temperature to 45 degrees Celsius, because above that, you get to the pain threshold, and if it's a long time above that temperature, you get skin burns. So that's the first limitation. The heating area, in this case, only the upper leg was heated, so you could actually consider whether the lower leg should be heated as well, but we didn't want too much surface to avoid heating the core temperature. Now, when you use electric heating, then you have the problem that, for example, if somebody puts a blanket over the trousers, the temperature will rise because it will deliver the same amount of power, and that means you can overheat and you could have a skin burn. So you need quite a big safety margin to be sure that people don't overheat, and therefore it may not be that optimal. So we looked at an alternative, and an alternative is have water heating, and the same suit that I showed you earlier when we looked at heat extraction was used for this, and we looked whether it would be more efficient to use a water heated trouser to do this. An advantage is that if you perfuse the water heated trousers with water, for example, of 44 degrees Celsius, it doesn't matter how many blankets you put on or whatever you do, it will never get warmer than 44. So that's you need a smaller safety margin, and that means you can turn up the temperature quite a bit higher. Of course, the downside is if you perfuse this with water, and of course this was clearly a setup which was for a lab experiment, you would need to develop a system that can do this, and that's of course a lot more complex than with just simple electric heating. So that was also why most of this research is published, and this was Margherita Recuglia's paper looking at post-warm-up muscle temperature maintenance. She looked at blood flow contribution, external heating optimization, and I will only show you some data on the last thing. So what we have here is the experiment repeated. So now we had a pre-temperature, so pre-warm-up, and the two lines you see here is a measurement of muscle temperature, quite superficial, 8 millimeters deep, and more deep, 28 millimeters deep. So you see at 8 millimeters deep, it starts roughly at 32 degrees Celsius, and at 28 millimeters deep, it starts at 35 degrees Celsius. The warm-up pushes this up to above 35 for the superficial one, and above 37 for the deeper one. So that's 2 to 2.5. So it's for the superficial one, it's a substantial, the biggest increase. And what you see on the right-hand side, when you have the data points after the rest period, so with the water-perfused trousers, you see here we have abolished the drop in muscle temperature. So the muscle stays at the same temperature, or even superficially gets a bit warmer compared to after the warm-up. So unfortunately, because we did some other work here where we also occluded the blood flow to one of the two legs, we couldn't do a proper performance test here, but just showing that the muscle temperature can be kept a lot hotter in this way shows there is quite a bit of scope for optimization of the heated trousers that we originally had. So we've used this in this case in track cycling. So what about other sports? So we did one project which looked at swimming, and swimming typically do a warm-up 35 to 45 minutes before the race, so a much longer period. So not like with the track cyclists when only an accident will cause this, but this is a standard procedure. And we know that with swimmers, especially freestyle, most of the power is generated by the upper body, and that means that we need to heat the upper body rather than the legs. So this is published by Emma Wilkins, looking at improvements by muscle heating in swimmers. So in this case, we had a heated jacket, which is shown here in this infrared image. And given that 90% of maximal freestyle velocity is produced by upper body muscles, we felt that that was the way to go to keep those heat. So a similar protocol, the people would do the warm-up, then they would wear this until the race, and then they would do the race. And here you can see the body temperatures with an infrared camera. So on the left, we have pre-warm-up, then we have post-warm-up, so that the warm-up is in water, so actually people cool down a bit. Then we have the recovery period. So the third image here is the recovery period in normal clothing and tracksuit. And on the right-hand side, you see when there's heating in the recovery, and you see the upper body is much warmer than normally. So the question is, does it have an effect on performance? So we use high-level swimmers, warm-up, then 30 minutes rest with or without heating, and a performance test. We did plyometric press-ups as one of the measurements, and there was a starting strength, peak force, and peak concentric power were all higher, significantly higher in the heated condition than in the unheated condition. But more importantly, what happens when you swim. And they did a 50-meter freestyle swim, and we found firstly a faster 25-meter split. And then we also found that finish times were faster as well. So over all people, so we had 8 males and 4 females, over all the participants, we had 8.83% improvement. And you have to look at that relative to that 0.4% improvement is considered a relevant improvement in swimming. And if you looked at the males only, as we do in the next slide, we see the improvement was roughly 1%. And we also observed higher stroke rates and higher stroke counts. So looking at the data for the males and the females separate, unfortunately, we only had 4 females. So that was, we knew that was at low statistical power. But we see that in the males, we see a significant reduction. And with the females, we see that there's a mixed bag with 2 people reducing their performance and 2 people improving their performance. But anecdotally, when we spoke to the females and the males, we found that the males found the heating quite okay, but the females found it extremely uncomfortable. And that might be an additional reason why there was a mixed bag of performance improvement. So we do think that for the females, the setting of the heated jacket was too high, they felt too hot. And if you introduce discomfort in athletes before they have to do a race, that is definitely is a negative thing. So we, in the future or for practical application, you will really have to make this adjustable by the individual athlete. So conclusion for muscle heating. Local muscle heating for muscle temperature maintenance has clear benefits for various explosive and sprint-related sports. So it's not for a marathon, it's really for short, quick bouts of exercise. What we haven't seen, at least I haven't seen it come up, is introduction of this, for example, in high jump, long jump, which I think would be a logical step because they're also explosive sports. And very often you see people doing high jumps, for example, waiting out on the track and just standing around, and I'm sure that is not beneficial for their muscle temperature. So a different topic or a different area that we worked at was body mapping for sports clothing development. So that's much more for the consumer market than for the high-level athletes. And I'll just give an example of some of the work. So when you think about clothing and heat loss in the heat, what we want to do with sports clothing, we want to minimize the vapor resistance, so as much evaporation as possible can take place through the clothing. We need to have moisture management, so absorption of sweat and transport of sweat, and ideally targeted microclimate ventilation. And when you ask that for a designer, of course, the big question is, which areas of the body should they apply special fabrics to? So one thing that would help with this, when we talk to designers, in this case with both Adidas and Decathlon, is if you know how the body distributes its sweat, that means you can adjust the sweat management for different body parts and for different sweat production. You might be able to optimize the clothing. So the question to us was, can you create body maps of sweating distribution for different population groups? So we've done a lot of work on this, and these are the earliest papers, 2011, 12, and 13, but we still are publishing in this area in the last 2 years. And the way we're doing this is we're using a technical absorbent method in where we have a material, as you see here on the right-hand side in the slide, the white patches. They are a technical absorbent, which is material is when it comes in contact with fluid, it absorbs it and it doesn't release it anymore. So in this case, you see there's lots of patches cut to the size of the person. And in the experiments, we would have to do 3 experiments for one body map, because we only would cover a third of the body at one time for a very brief period. So we don't want to cover more because that would impact the body temperature too much. So we have short measurement periods. We only would put these absorbent materials on the skin for something like 4 or 5 minutes. And we make sure that we use only a small part of the absorption capacity of this material. So with the highest sweat rates, we stayed below 5% of the absorption capacity of the material. And that was to avoid having wet materials on the skin, which of course could influence sweat production. So this is some of the results. So this was from the first study, which was male athletes. So you see a regional distribution of sweat rates, and this is for 55% VO2 max, and the front of the body is on the left and the back is on the right. And strikingly, what you see here is that the back of the body sweats a lot more. So the back or upper back along the spine and the lower back along the waist has a much higher sweat rate. The forehead has a very high sweat rate, which was not surprising, but the one on the spine was clearly a new finding. And then you see that also the rest of the body has quite specific distribution of sweating, where the hands and the feet have low levels of sweating, whereas the lower arm and the lower leg are higher sweaters than the upper arm and the upper leg. So when we looked at higher work rates, so that's what you see here. So the middle picture is now the front at the high work rate and the right-hand one at the back at the high work rate. You see still a similar pattern. It's just shifted up to much higher values. And just to give you an idea of the values, at the forehead, we're roughly at 1700 grams per square meter per hour. On the upper back, around 1200 grams per square meter per hour. Whereas on the hands, for example, we're now at around 250 grams per square meter per hour. So massive differences between the different body parts. So we don't really know the cause of the sweating pattern. It's not the number of sweat glands in the different areas, because they don't match up the sweating. It's not related to local skin temperature, because normally when we have a higher skin temperature, we expect more sweat. So we looked at all these different factors to see which of these would influence the sweat pattern. So it's not sweat gland density, it's the production of individual sweat glands. So we handed these data to Adidas, and they used this then to look at different designs. And for example, these are some of the designs that originally came up with, where along the spine, they have specific ventilation fabrics with, you see they're very open to improve the ventilation of air and thereby the amount of water that can be evaporated. And they also had different fabrics in different parts of the body, which had different absorption characteristics. We also did this for females. So this was the male at 70% VO2 max, and this was the female. And you see very much lower sweat rates in the females, which again is quite striking. But in this case, the females were a little bit lighter and a little bit less fit. So at 70% VO2 max, they would run a bit slower. And also due to the weight, they would require less energy, and therefore they produce less heat. So in some ways, that means is the biggest reason for the difference here is that the females were producing less heat and therefore need less sweating. So if you do that at similar VO2, which is this comparison with the left-hand side, it's the low work rate for the males and the high work rate for the females, you already see that this comes much closer, and the patterns when these are normalized are not that different between males and females. Recently, we've been doing some work on older people to look at whether they sweat differently, and we see indeed mainly differences in the legs, which have reduced sweating. And we also have just recently looked at prepubertal children, which you see here on the right. And I have to warn you that the scale for the sweat rates is very different. So the adult one goes up to 1200 for the dark red. In the children, it only goes up to 200. So you see that children sweat a lot less per square meter of body surface area than the adults. So that's the interesting question there, is whether that's due to an incomplete development of the thermoregulatory system, but also in part it's again due to the lightweight of the children, where they generate less heat when they're running. And this type of research then also leads to products. And for example, Adidas has produced a special climate-cooled training T-shirt for kids based on the information that we delivered them with the different sweat rates. So to summarize, what our experience is that working with industry provides great opportunities in a number of different ways. So firstly, it helps us answering relevant real-world questions. So we're not just working theoretically, but we're really directly influencing what will happen with their products, and they come to us with questions that they have received from the field. Of course, a very positive thing is it provides funding for PhD students. We all need funding for PhD students. This is a stream that has been very effective for us. And it also, in addition, provides enterprise funding. So in addition to the PhD projects, sometimes we do projects that, for example, need to be done very quickly. And we run that through enterprise, which means it's consultancy-based work. And really good because in the UK, the system for evaluation of universities is very much based on, do you have impact in the real world? And of course, if you have a product that's based on your research, that's your direct evidence of impact. Considerations: if you work with industry, make sure you negotiate confidentiality at an early stage, because you don't want a PhD student to work for 4 years and then being unable to publish anything. So negotiate publications. What can they publish? And in our case, that has always worked out very well. Sometimes we had to wait for a year before we could publish, so the company had the advantage. But in most cases, we're able to publish quite quickly. And I would say, with working with industry, limit actual product testing to ensure independence, because of course the research you do, while it's driven by what industry is asking for, you should not be part of the industry. So you have to remain independent and be really academically independent of the industry. Okay, that's my overview. I hope that was interesting for you, and I'm looking forward to any questions you may have. Thank you very much.
Thank you again to Professor George for a very insightful presentation on improving sports performance with sports clothing. And now I'm going to open the floor for any questions from the audience, and also to invite Professor George to unmute his microphone to address the questions. Professor George, are you here?
Yes, I am. I hope you can hear me well.
Yeah, very loud and clear, crystal clear.
Excellent.
Okay, so perhaps I can start with the first question. From your presentation, Professor, I think this is the essence of what we've discussed during the first day of the conference and how it should be portrayed. And by that, I mean academia giving the support in terms of research to the industry to take action. So the question that I have here, Professor, is how did this all started? I mean, did you and your team approach the industry with an idea, or was it the other way around?
Yeah, I think we've been very lucky in that respect. When I worked in the Netherlands still, we were indeed approached by somebody from the industry. And that was actually a person at the time who worked at one industry. And so they asked lots of questions about science. And then a while later, they came back and said, well, actually, you could really help us with this by giving us advice. So in the first couple of years, we mainly contributed by meeting up with industry and almost had like brainstorming days. And that worked really well. And then by chance, some of these people started moving into different industries. So they started changing employer, but still came back to us. So I think the challenge with this type of work, of course, if you work with multiple industries, is, of course, you cannot share ideas from one industry with the other one. So that's where you have to be really careful. So in our case, we've limited the number of industry that we work with. Or the other option is to distribute the different industries with different academics in the school. So you almost don't talk to each other about the projects.
Because of the
And
confidentiality. Yep.
yes, because that's really important, of course. And I think the really nice example that we had with Adidas and Decathlon is that, of course, they were both aware. We made them both aware. We first asked, is it okay if we tell the other people that we're working with you? And then we more or less negotiated the topics. So we were never working on the same topic for both industries. And so we really defined the area we were working in. And in practice, that often also had a spin-off later on the other industry. So it worked really well for the industry as well.
Thank you for that. All right. Perhaps another question from the floor. This is from Dr. Shariman. Hi, Prof. Thank you for the inspiring keynotes. I have two questions. How comfortable are the cyclists when they wore those suits? That's the first question. And the second question is, what's your thought regarding the 4D textiles technology? Textiles that are programmable and can change shape or function over time by the influence of a stimulus from force and height. Are we close to see this technology being used widely in sports?
Okay, so I'm not sure whether the question is about the cooling suit or the cooling materials or the heating. So I assume it's the heating, given that they're talking about a suit. So with the electric ones, the temperature was around 40 degrees Celsius. And actually the athletes that used them in the Olympics were quite positive about the work. So so they worked really well. With the swimmers, as I mentioned, the problem with the swimmer suit, we used a commercially available jacket, heated jacket, which was used by motorcyclists. So that was not a specially developed product. And I think what we didn't control very well there is the power input. So with the trousers, we clearly had very well controlled temperatures on the inside, whereas the student that used the jacket for the swimmers actually ran them at full power. And we didn't realize that until at the end, when we indeed got the feedback from the females that they didn't like it because they felt it was too hot. So I think if you do development like this right, you have to consider this and really need to control the temperatures on the inside of the suit to make sure you're not overdoing it. The males didn't mind, and in the males we did see the improvement. The females didn't like it, and we didn't see an improvement there on average over the females. So that's a really important point.
For the second question regarding the 4D textiles technology.
Yes, that's really interesting. And over the years, I've seen many materials, high technical materials not really come onto the market, but being presented usually in materials journals, which are developed by textiles departments. And I think what's slightly disappointed for me is that I have not seen many of those specialist materials transition from the research into actual applications. So I do think for the future there will be relevance in those new materials. But I think there still is a problem to move them from a product which is produced in small scale in a research lab to a real life application. And just to give you an idea, so about some of these, we all talk about smart materials, smart garments. The biggest problem still after many, many years with these garments is the washing. And of course, if you do sports, washing is an essential part because you don't throw away your garment after one time. And it's still, so it's often the very basic problems like washing and electrical connections, and do you need to take the material out? So if you had the heated trousers, for example, and you would need to take the heating materials out each time you wash it, then you have a problem, or it will not be used as much because it's too complicated. So I think I think the question is whether we expect to see this technology being used widely in sports. Yes, but it's coming in much slower than I think I would have hoped.
Right. Thank you for that. And perhaps I can take one more question that's also relevant to that previous question, which is, it is known that temperature affects performance. In a hot environment, you need to promote heat loss, and in cold environment, prevent heat loss. Is there any room in the future, or if it's possible, for a clothing design to suit the best of both worlds? What's your thought on that, Professor?
Yeah, that's a really interesting one. And it's something we thought of pursuing, but haven't really had the time. So the question is, what happens if you cool the upper body and heat the lower body? So for a cyclist, of course, where the leg muscles are the important ones. And I think that's going to be a really interesting question for the future. To have that mixed approach, trying to get the best of both worlds. with the muscle heating, we don't want to increase body temperature overall. And to do that, you could then put a cooling system on the upper body. There is a risk there that people might find that a very contrasting sensation, because that people usually don't like being both cold and warm. But that's really an area that needs to be investigated.
Thank you, Prof. Another question by Associate Professor Dr. Raja. Great keynote presentation, Prof. What is the best muscle heating approach we can apply during halftime interval in intermittent sports, for example, football?
Yes, I have no research data on that, so that's purely a personal view. So what we see in most applications with sports like football is that people are quite warm when they come out. So again, they often need to cool down in terms of overall body temperature, but you want to reduce the cooling of the muscles. So I don't think you will need heating there unless you're in a really cold climate. So just having a standard insulating trousers, I think, would be quite sufficient, because the whole body is already hot. I think in football applications, where I would see the application of this type of material is really of people, of the players that are on the bench, that will swapped into the game. That would really help to have their muscles preheated even before they actually start their warm-up. And we see this in rugby, especially here in the United Kingdom. When you go to a rugby game, very often it's rainy, it's cold. And I think that's really where the benefits could be for the players. So their muscles are more ready when they start to warm up and go into the game.
Great one, Professor. Thank you for that. Perhaps one last question that I have directed to me here to give to you, which is, working with top sporting industries such as Adidas and Decathlon promotes a focus-shifted outcome by giving the industry what it needs. Is there any current or future projects that you can disclose? I think it's probably confidential, right, Prof?
Yes. So that's unfortunate. We usually can talk. We've agreed with most of the industries that we can talk about projects that are past. And I think at some point I said that sometimes we have a 1-year embargo. So, for example, when these heated trousers were developed by Adidas with us and British Cycling, we agreed all to wait until the Olympics before that was made public and then later on published.
Was it always the case of late publications, Prof, for the industry to have an advantage over product release? Or is there a fine line on what can be revealed to ensure the progression of the PhD students, for example?
Yeah, so we always, in all discussions with industry, we make it clear that it's important for the PhD students to get a job later to publish. And so we've been very lucky with the partners we have had. What we also try to do is not to work too much directly on the product. So probably the heated trousers were closest to actually being directly involved in the product. But most of the work that we've done is the more basic research, like the sweat maps, the temperature maps, and we created sensitivity maps. And that there's the industry uses those to change their designs, but usually they know when that comes on the market and then they advertise with it. It's open and public anyway. So usually they just want the advantage to be the first company to bring this on the market, and then they're happy for us to publish. So we've really been very fortunate with our partners in industry.
Great. Thank you for that, Prof. So if there are no more questions, thank you so much, Prof. Dr. George Havenith.
Okay. Have a great day.
You too, Prof. Again, thank you so much to Professor Dr. George Havenith for a very interesting session. And we thank you for taking the time to share with us your vast experience in the field. It is truly much appreciated. Thank you so much again. To my respective audiences, that marks the end of the second day of the conference. Be sure to join us tomorrow morning, starting at 9 a.m. for the parallel sessions, as well as keynote presentations. We have more interesting topics lining up for tomorrow, and you surely wouldn't want to miss it. And with that, thank you, everyone. Stay safe wherever you are, and we'll see you tomorrow.